I'm going to go ahead and introduce some information about HYDRAstor. As I mentioned, when we did this last time, about 4 years ago, we talked about HYDRAstor exclusively. In fact, I see one familiar face from that particular event.
That is correct.
So you were there 4 years ago. And I see a few familiar faces in the front. But it's nice to see also on the attendees as well. In essence, 2/3 are people that I haven't met before. So that's good. HYDRAstor, I mean, some of you may be familiar with it, some of you are not. It's a scale-out global deduplication storage system. We refer to it as the fastest deduplication storage system. That's based on scale-out performance. So I'll show you how that translates. But actually also with an additional enhancement that we did this year, which I'll talk about, and also Nabu will talk about, which is a dedupe transfer, we actually also can claim the highest single controller performance as well. So for a single controller, we provide the highest throughput, as well as obviously also has the highest scale out in the industry for this class of product. And based on that, that's one of the factors that also contributed to winning best in class for the Buyer's Guide last year, as well as the best storage solution on the 2014. You will find a lot of vendors display this logo, but there's only one category that's for storage, and this is the one. So that's the HYDRAstor was the winner in this one. The areas that we key on in HYDRAstor when we first started, I mentioned there was around 15 R&D labs worldwide. We actually started the HYDRAstor technology in our R&D lab in Princeton, New Jersey. So this actually is based on that, and back in 2000, that's in 2002, so about 12 years ago. In 2005, we started more of the development and packaging towards the product, and we first launched this product in 2007, the first generation. When we did the event 4 years ago, we were actually showing the Hydra 2, the second version. Today we're actually shipping the 4th generation, so you'll see some of the differences in there. I'll also talk about them. Key area that we focus on is scalability limitations of traditional approaches. I'm sure all of you are familiar with more of the scale-up approach, where you have either 1 or 2 controllers on the front end, and then you can add so many storage shelves behind it. The limitation with that is obviously if you're maxed out at the controller side, even if you're allowed to add additional shelves, you won't, because then your performance will suffer. And vice versa, if you're maxed out on the number of shelves, even if you can support from a throughput perspective, you will need to have an additional device. So when we talk about things like storage virtualization, with the scale-up approach, you cannot share those resources across or virtualize the resources, and that's one area that we wanted to address with a scale-out approach. The other thing, the more of these separate devices you have, not only do you lose the efficiency on the utilization side, but when we get into things like deduplication, a thing that matters is scope. How much of your infrastructure can you fit into a single dedupe repository? And the key thing is, the more of these separate devices you have, if they're independently managed, statistically, you're guaranteed at the chunk level, in essence, to have duplicative data across those separate devices. And if there's no communication, not only do you use underutilization, you also lose in the efficiency. The bigger your system gets, if you're talking about, let's say, 10 terabytes, 20 terabytes, 50 terabytes, lots of vendors can do that in a single device and do deduplication locally for that device. But when you get into hundreds of terabytes, or you get into petabytes of information, there are very few or actually no other ones that can do it to the level that the HYDRAstor does. In essence, this one actually kind of captures what I'm talking about in terms of local versus global. For those who are not as familiar with this, local deduplication, you can have it done at a volume level. So you can have a storage system where each volume has its own dedupe repository. And if you write the same information to 3 separate volumes, you'll end up with 3 copies. Local per node or per appliance means if you write from multiple locations, and these could be remote locations as well, replicating, anything that's written to the box will be deduplicated across the entire box, but that doesn't make it global. Because now if you have a second box sitting right next to it and you write the same information to that box, all it cares about is what was written to it, so you end up again with multiple dedupe repositories. So what we talk about with HYDRAstor is more of the global approach, where you can have multiple sources writing into the system through multiple front-end nodes, and we'll show you that in the lab as well, and the demo that Nabu and Sanjay are doing. And everything is deduplicated. This is all done inline before it ever hits the disk. but it is all, you're guaranteed, anytime you write any information, you're guaranteed a single copy across the entire system by the time it hits the disk. So that's kind of the approach that we do. And then the other one, the other key area for HYDRAstor is around resiliency. Since we have implemented this, we ended up implementing this kind of with an underlying object store on the back end. And in fact, some of you have also seen over at the Object Store Summit as well, is really when you get into things like backups or archives where this becomes your gold copy. If you have, this example shows for backups, if you have a full backup, then multiple incrementals, then another full, all of the similar chunks of data are going to resolve to a single chunk, which means now your data actually represents, each chunk of data represents a lot more information. If you lose that chunk, you didn't just lose yesterday's backup, you lost pretty much all your backups. So now it becomes much more critical to protect this at a higher level. And also as drive sizes are increasing, and we're shipping 4 terabyte drives and people are shipping 6 terabyte drives and going into 8 terabyte drives, it takes longer and longer with traditional RAID to recover that data. And that's both disruptive to your normal I/O and also increases statistically the chances that you will have a second failure or a third failure. And then what do you do as far as protecting your data? So what we have with HYDRAstor, we have a scale-out architecture. We can actually increase either throughput or capacity. Back when we did this in 2010, we were actually shipping accelerator nodes and storage nodes. So back in generation 1, 2, and 3, you can either increase throughput or you can increase capacity. With generation 4, which is the current shipping product, which we'll also show you in the demo, we have the hybrid nodes, which in essence, at a physical level, they combine both the accelerator node and the storage node function. Both of those virtual functions sit in that hybrid node. So in essence, with the current infrastructure, you can either increase both throughput and capacity or just increase capacity at a lower cost. And these actually, as I'll show you on the next slide, they can actually interact with one another. So the new hybrid nodes can actually also interact with the old accelerator nodes and the old storage nodes. Everything you see over here, I mentioned at the top of the presentation when we talked about NEC as a whole. We also ship general purpose servers and storage rich servers. As such, we're actually using our own servers. These are industry standard servers. There's nothing special about those servers, but those are high quality servers. We're the manufacturer for that. So we ship all the hardware that you see over here. And then also all the software is all developed by NEC technologies. From a management perspective, we'll take a look at the user interface. We'll do the demo as well. But very easy to set up. We actually configure it to customer environment. Once we actually deploy it in the customer environment, typically less than an hour up and running. Unless you have to attach multiple racks together and have more of a rack and stack or going to customer racks as opposed to the HYDRAstor racks, that's going to add time. But otherwise, it's very simple to get going. For those who are familiar with VTLs, this is not a VTL solution. So this is just CIFS or NFS connectivity internally. And then also we have OST connectivity for semantic net backup.
What level of OST? Are you supporting AIR or other functionality?
Yes, I have a slide on that. Right. We'll talk about that, and we'll also do part of the demo also encounters that for OST.
So, I didn't ask maximum configuration instead. So you can start with one, but you can...
Up to 165 nodes.
165, okay.
I will show you that on another slide.
You're not going to show that in the demo?
I do not have enough budget. I do not have that $20 million or however much it is to buy that. But let's just say I have yet to sell a 165 node system.
So it's a good question then. What is the biggest system that's out there?
So today the biggest system in the US is currently 50 nodes.
50,
yes.
Okay.
For
actually how many petabytes or terabytes?
I have to calculate because it spans, I was just going to say, it spans 2 different generations. So generation 3 actually had 12 1 terabyte drives each, so 12 terabytes each node. And then generation 4 has 12 4 terabyte drives, so 4 times as dense. So it really depends.
So a node is just one single shelf of disks, basically?
But it's a full server. So it comes with a motherboard, with so 2 CPUs.
You can't scale up with you can't scale up with this to multiple shelves of disks?
No. So what I mentioned over here is you can actually add either hybrid node, okay, or you can add a storage node. Even the storage node will be a full-blown server. It's not a dumb shelf, but in essence, it just adds capacity.
No additional add extension shelves to any of the nodes.
No extension shelves. Everything always, I'll show you why, because part of the compute, and then in order to deliver linear performance, we always talk about linear performance scalability. We have to always, whenever we add capacity, a lot of times people say, well, if you add capacity, you're going to see degradation in performance. That's why whenever you add capacity, you're also getting 2 additional CPUs, and you're also getting 96 additional gig of RAM. So this actually ensures that we can do that. The other thing I wanted to mention over here is also self-tuning and resource management. So on the back end, we actually go ahead and all the background operations, we have full control over that. We have certain default policies that we establish, but then we can also change those policies. We can change priority levels. We can change the percentages of resources. This is all runtime changeable, but typically we stay with a certain policy, and we have several configured policies that we allow the user to choose. And then we automatically also ratchet the level of resources based on the situation. For example, if you took a 1 drive failure, no big deal, that's a normal failure. There's going to be reconstruction in the background. If you suddenly took a 2nd drive failure or a 3rd drive failure, we automatically ratchet more resources to try and do that recovery to get it to a more normal operation. This slide and the next slides are key for HYDRAstor in terms of some differentiation. One of them, this goes back to Ray's question about erasure coding or versus RAID. This is something that since day one, since we first launched this in 2007, we've been using erasure coding. So at the time when, in fact, just this week when we were at the storage decisions, and then later on we had another regional seminar I was at yesterday, I asked people if they know what erasure coding is. Usually I get 1 or 2 people raising their hands. Hopefully, how many of you are familiar with erasure coding? Okay, I like that. I like this. So this is much easier. So since we have a back-end object store, this allows us to do this fairly easily. Our implementation is based on 12 fragments. So 12 fragments total. And then we let the user decide on a per file system basis whether they want level 1, 2, all the way to 6. So anywhere from 1 to 6 concurrent failures and still maintain full access to your data. And then we do the distribution, and you can mix and match different file systems. Whenever you create a file system, the default is 3, but you can change it. So 3 out of 12 is kind of the sweet spot that we find from customers. This example shows you what happens if I have at least 4 storage nodes in the back end, and at level 3 protection, we will take any chunk of data, distribute it into, split it into 9 fragments, and then automatically calculate the 3 additional fragments of protection for the total of 12, and then we'll distribute it across as many storage nodes as possible, up to 12 if I had enough of them, with each one on a separate disk drive.
Do you also have the the concept of dividing data on different racks, or not only nodes? So if you have a...
So we do it across nodes. We do not split it across whether it's sitting on one rack or another. Because one other thing we also do is we actually distribute data automatically across and balance it across all the nodes, across all the racks, right? So there's no hotspot of any data I/O coming in. So if we try to restrict it to certain portions, now you do end up creating those hotspots. So we actually just always, as you'll see on the demo, we actually have very well-balanced distribution.
Are all the nodes disk only? Or are there SSD nodes?
These are disk only, and all the performance numbers are all based on the fact that of those disks and everything I'm talking about, there's nothing that's different across.
You mentioned CIFS and NFS, so SMB3?
No, we do not support SMB3.
2?
SMB 2.1?
2.1?
This SMB
right now,
just 1, right?
Yeah.
SMB 1.
Well, it's CIFS.
What's that?
CIFS.
Thank you very much. Yes.
Hey,
Next call will support 2.
Right.
Well, you can consider 2 actually includes 2.0 or 3.0.
Yeah. Yeah, we get this question every now and then, but majority of our customers do use with SMB1 that we currently have and do not have an issue.
NFS version 3 or?
NFS version 2, I believe. 2. Yeah.
That's right.
Have to blow the dust off your old notes, Ray.
Sorry?
Have to blow the dust off your old notes. I had a question. So Ray asked about that they're all disk. I'm not quite clear personally about there was on one of your slides where you had the hybrid nodes, the
storage nodes,
performance nodes. Yeah.
Yeah.
I may have missed something. What's the difference and what's the role of those three different?
Sure. So in the original platform, we had accelerator nodes that did not have any user data on them.
Okay.
Okay, just purely for processing SIFs and NFS, and part of the deduplication process, I'll talk about that, is happening in there.
Yeah.
And part of it happens as the data flows into the storage nodes.
Okay.
What ends up happening is you're losing the density of the physical space. So we figured, let's just, from a density perspective, let's just incorporate both an accelerator node function and a storage node function in that single 2U.
And that's
server.
what you do now as a hybrid node?
As a hybrid node.
Okay.
So it's a hybrid of both the accelerator and the storage.
Yeah.
So over here it's either hybrid node, which gets you one of each in essence, or just a storage node.
Sure.
And they're all 2U servers. Yeah.
So is it a challenge when you've got like potentially hundreds of nodes clustered to manage, like, you know, when you said you dedupe as well inline?
Yes.
Globally, which is awesome, but I'm just trying to get my head around how you do that on like 100+ nodes without taking a huge performance hit.
Have you seen my next slide?
I have not seen
that. That is the next slide. Let me just finish on this one, and then you will get your wish, and let me know if it addresses your question.
All right.
But I do know it's the next slide.
Okay.
All right. I hope.
Yeah.
Okay, but over here the key is if you have at least 4 storage nodes with that level 3 protection, each one will end up with 3, which means even an entire node can go down. You just lost all 12 disk drives. You still may not only not lose data, but you maintain full access to the data. So full read-write, even if an entire node goes down. If I had at least 12 of these nodes, and I'm at level 3, I can have 3 entire nodes go down and still maintain full access to all my data. So the bigger the system gets, the more of, but if it's a smaller system, you just have it at the drive level. So going back to the question, how many can I start with? I can start with 1. Even on the 1, we will actually do erasure coding across it. So you can have 1, 2, but on 1, we actually limit it up to 3 levels of protection. So you can have up to 3 disk drive failures on a single one. Some of the other advantages, which if you're familiar with erasure coding, no idle spare drives. All the drives are working for you all the time. If you need to do reconstruction, that happens on the remaining disk drives. When reconstruction happens, not only can we control it, as I mentioned, from the resource management perspective, but also from the data itself. Only the data fragments that were lost, those are the only ones getting reconstructed, not the entire disk. So with RAID 5, RAID 6, you actually have to wait for the entire geometry of the disk to get the...
So if I have a single node system, the erasure coding works at the drive level. Once I have more nodes, does it then work just at a node level, or does it still...
Correct. I mean, let's say you only had... Actually, let's say you had 2 nodes at that point. You're still doing it at the drive level, but you don't have enough nodes for this distribution to be able to take a node failure.
With that distribution, okay, once you've
we automatically, the way we distribute, and when you add nodes, we automatically rebalance data. So we actually shift fragments to try and maximize the level of protection.
Okay.
So by the time you reach that 4th node, we will automatically get you to that level. Yes. So that happens automatically. Any other questions on this slide before we switch to his favorite slide? Okay. All right, so this is a picture, the logical view of our deduplication, inline global deduplication. As I mentioned, another big differentiator for HYDRAstor. In this picture, I'm showing 2 accelerator nodes and 4 backend storage nodes. The reason being is, in essence, that gives you full HA. And why is that? On the accelerator node, we have full failover capability across, so we can fail over file systems to another node. They can both be active at the same time. And on the back end, as we talked about the erasure coding, if I'm at level 3 protection and I have at least 4 nodes, then I can take any single node failure and still have full access.
And the intercluster connect, is it InfiniBand or LAN?
Oh, you're going to love it. It's all 1 gig connectivity, 1 gig Ethernet.
1 gig Ethernet.
It is not a bottleneck today. Our performance numbers are actually, there's always a bottleneck somewhere, right? Today, it is not a bottleneck based on current technology. We anticipate that probably in Hydra 6, not Hydra 5, it will become a bottleneck, at which point we will switch to, most likely to 10 gig. But today,
is it like a
so it's actually multiple connections. It's 4 data connections per node.
Yeah.
So 4 1 gigabit connections. But since the dedupe happens on the front end before it even flows there, a lot of the data never even have to hit the actual storage side. So that's what allows us to maintain that level of performance with much fewer physical
connections. You try to
connections.
isolate that network from the other traffic going on in the data center, or is it?
This is all internal. Nobody talks to it.
Other
You
than
only
you guys.
talk, yeah. You only talked on the front end. We present on an accelerator node. We present you some either 1 gig or 10 gig Ethernet connectivity. On the back end, this is all our internal connectivity. So all the accelerator nodes and all the storage nodes are interconnected via that private. And in fact, the 165 nodes that I mentioned, the maximum, it's really based on how we design the back end network. There's nothing limiting about the architecture that doesn't say we can't go to 300, 400, 500 nodes either. So it's really more from in terms of how many connections with each one of these getting 4 plus 1 for management. That's 5 connections internally per node.
On the internal interconnect, is that TCP/IP, UDP, or something your own homegrown?
Internal?
TCP, yeah,
TCP.
TCP/IP. We have like not only protocol, but the base.
The base level is TCP/IP.
Okay. So actually, let me ask you guys a quick question. In the current implementation where I have hybrid nodes, to have this kind of an HA config, how many nodes do I need? Who's the first?
4.
Thank you very much. 4. Because the hybrid node includes one of this and one of this, one of this and one of this, and then you just need to add 2 more storage nodes. So you can actually...
Does that mean I get a prize or something like that?
I'll try. Well, you already got your prize, but I'll try and figure something else for you. You get first dibs on lunch. Okay, but going back to the question that came before I showed this slide, in terms of how do I maintain performance? So let me explain over here using this picture, what is the difference between what we do versus some of the other ones that have a single controller with just back-end shelves. So in both cases, when you do things inline, you have multiple file systems mapped here. You have multiple file systems mapped here. So over here, if this is a single controller, we are going to do the fingerprinting and chunking of the data. We will calculate the hash value of that chunk of data. This is where it gets different. On the single controller type systems, the scale-up approaches, over here within this controller, they have to determine, is it a duplicate or not? Do I actually just write the metadata, or do I just write the entire payload? Which means now you're limited at the physical level in terms of how much CPU and how much memory you can fit into a single server. Okay? And this is why the other vendors that do this will have a smaller model and a bigger model and a bigger model, with the biggest one being the one where they can fit the most memory and the most CPU. Okay? And otherwise, I mean, yeah, you can put more storage behind it, but then performance will dive. In our case, once we did the fingerprinting and chunking and we calculate the hash, rather than try and fit this entire hash table lookup over here, we just do a routing table. So we divide the hash table into multiple ranges, okay, depending on how many backend storage nodes we have. Or in the case of hybrid nodes, it's either storage nodes or hybrid nodes. Total storage node virtual instances. In this example, I have 4 of these, so we will split the hash table into 4. And in essence, you end up with a distributed hash table instead of a localized hash table. So now over here, I don't need to know, let's say it falls within this range. I don't need to have enough memory and to know, is it a duplicate or not. All I need to know is if it falls in this range, I forward it over here. Okay? And it doesn't matter if it came through one file system or another file system here, or a different file system over here. If it falls in this range, it automatically gets to here.
And the storage node is responsible for the hash space.
The storage node will then, for its own portion
of the hash space,
will decide, hey, is it a duplicate or not? Regardless how big my system gets,
right,
it will always get funneled to him for that portion.
Right.
Okay? And then if it's a duplicate, all he needs to do is just write the associated metadata tags, right?
So,
and distribute it with the erasure coding to protect it.
Do you
Yes.
do really strong hashes, so you never have to do like a bit-for-bit lookup, or?
So we do a little bit of both. I mean, we do use SHA-1. SHA-1 is pretty much the accepted kind of de facto in the industry.
A single SHA-1 or a single SHA-1 or multiple?
Single.
And what bit level?
So SHA-1 is 160 bits, right? It's 20 bytes. SHA-2 is 256, but that would slow you down.
Higher. Yeah.
Yeah.
SHA-1 isn't accepted as a faultless.
Yeah, pretty much, because you have a higher chance of taking more than 2 failures on RAID 6 than you do of like a collision or something like this on a SHA-1. So I mean, people use RAID 6 all over.
I've seen failures on RAID 6 too.
Yeah,
Of course, I know, and that's what I'm saying. But the statistics, I mean, we can look it up. It's like 10,000 times as more likely that you will hit this versus
I can generate a collision on SHA-1 in under an hour.
Okay.
So it's just not, I don't know.
I will tell you that we've been shipping this for 7 years. I have yet to see a single hash collision happen. What? So,
Could you detect a single hash collision?
so what we...
Could you detect a single hash collision if it actually happened? That's the question.
Well, I mean, you would have wrong data, right? You would have wrong data.
If they actually read it back.
Yeah, that's the
Yeah,
thing.
if you read it back. So we have yet to see that
Chance of getting the
occur.
right data, though. You know, they'd have to read all of it back. Yeah,
Ticking
Yes.
time bomb.
Yeah. Ticking time bomb.
Is it not?
Well, that's the same thing as ticking time bomb, that maybe a lightning will come and strike us and blow this entire building.
Hey, I'm worried about the aliens coming. Don't get me wrong.
Absolutely. So yes, you could worry about that as well.
But when I asked the question, you said you do a bit of both. So
In the background, we have a weekly scan. We scrub through the data. We actually make sure that the data is consistent, and it also matches the hashing as well.
all right. So it's,
So we do a background scrub as well, based as one of our background operations.
So you have some sort of CRC that you append to a
Correct.
to a data chunk to
Correct.
verify that the bits match the
Correct.
CRC.
but that's not the same as doing a bit-for-bit lookup when
No,
the
it's
data's
not.
coming in.
Yeah,
Okay.
we don't do it as you come in to constantly go across.
Right.
That will slow you down.
If you're finding that hash and if you find that hash that you already pre-calculated and stored, and you see that hash, are you basically just throwing out the data you have because you're assuming that hash is valid and already stored?
Correct. The actual payload will never have to hit the disk. So it will get tossed.
I'll look up
when we
at
pass the data over here, we're just passing the hash. In fact, this was an enhancement we made over generation 1. In generation 1, we passed the whole thing. Now, if it's a duplicate, at this level, you can toss the payload, which is why you don't need as much connectivity internally. You're actually tossing a lot of it away. And in fact, when we talk about OST and about things like dedupe transfer, which we'll talk about, this actually allows us to do that same type of thing, but all the way at the media server level.
And that hash table, the hash address space that one of those storage nodes is responsible for is replicated. So there's another version of that someplace else when it's modified.
Correct. So that's why I was just in the middle of saying is, once it's determined to be a duplicate, this one is responsible for that from a calculation perspective and distribution, but not to store on it, because if this one dies, you can't afford it. So even at that point, the hash will actually get erasure coded across multiple nodes. Okay, and then if it actually, go ahead.
The hash. Okay, I don't know if I quite understood what you were talking about there. I was going to ask a question. I'm not sure if it was answered by that. I'll ask it anyway.
Please.
The hash table. What protection do you have of the hash table? So
That's exactly what he said.
What he asked. So I'm just going to ask Ray a quick question. Is it cool?
It's cool, but it's erasure protected. It's written as erasure protected chunk, effectively across the rest of the back end. So
yeah, we actually have multiple. We copy
Ray
it.
says it's cool.
Ray says it's cool.
What happens when you add another storage node? Does it have to change who's responsible for what hash? Or you have to change the hash ranges and rebalance everything?
You must have been through my presentation before.
I have not been through your
Because after I was going to finish this thought process on this one, I was going to mention exactly that.
Okay.
So let me just finish that, because that is kind of key. If you actually find that it's not a duplicate, okay, meaning it is unique, at that point, it's going to request the payload from the forwarding node. Okay, so this means at that point, this node actually will take the data that it's holding, that payload, will compress it, and send it down over here, and then that gets erasure coded across multiple nodes.
So it's deduped, then compressed?
Of course.
Just checking. There's been a lot of discussion about that.
It was a tricky question. He said it in a tone that was going to make you say no, no. But
the
yes,
next question
absolutely.
is it encrypted as well on a self-encrypting?
We do no, actually no. M series has self-encrypting drives. HYDRAstor does not. But we do offer an encryption feature for encryption at rest, and you can turn that on, and then yes, the encryption will happen after the dedupe and compression. Yes,
of course. Yeah.
No, the reason that came up, you got that funny look, was because we've been in presentations where, well, some people do compress first and then dedupe, some do dedupe first and compress. So there's discussion about why you would do one or the other.
Well, there's only two
we like
ways.
dedupe first and then compress.
Yeah,
and
that
then
seems to
encrypt.
make sense.
And then when you hydrate the data, just the other way around. Yeah. So now going back into your question, so we already understand how the data flows inside, and we already talked about the erasure coding and how it's actually protected across here. So I mean, from that level also you can see that the fact that the processing of this versus this is almost opportunistic, that they happen to be physically on the same node, right? It's just a location that holds it. If I were to add a fifth node over here, okay, there are a couple of things that are going to happen automatically. One of them, with that node I get more capacity. So we will automatically take this data that's sitting here, not just new data, but also existing data, and redistribute and balance to take advantage of this additional node, this additional capacity. Which is why the more of these you have, the greater the protection, because now you suddenly have node level protection or multi-node level protection. And then at the same time, from a processing perspective, I just gained two more, in this case, in the current generation, 8-core CPUs, Xeon CPUs, and I just gained another 96 gig of RAM. So we will automatically redistribute this and carve it out into 5 portions, and take those components which are currently assigned over here that are carved into that fifth one, and move them over to here for processing. And now update all those tables across all the different accelerator nodes. And then obviously if I add an accelerator node, it will actually, or a hybrid node today, it will get the same mapping as everybody else.
So it looks like the storage pools are actually accessible through all storage nodes, but indeed they're actually not, right? The storage that's behind a storage node is directly accessible to that storage node, but cannot be directly
in terms of actual write to it, yes, but in terms of actually getting
logical
hashes and data coming,
it can go anywhere.
Yeah, you're right.
Okay.
Yeah. Each one writes to its own stuff. Yeah. Any questions on that? And does this address your question in terms of how we maintain performance?
Yes.
Is there a plan on changing the hashing algorithm, or are you keeping that because of legacy multi-generation support?
So we're constantly working. I mean, we've actually presented multiple papers at the, if you're familiar with the Usenix FAST conference. So we were selected to present at multiple of those conferences. There's several papers which we can make available, including the high-performance file system for HYDRAstor, as well as things like bimodal chunking. So there's several things we're doing on the back end in research in terms of improvements and some additional enhancements or anchor-based chunking, etc. So we are constantly looking at additional ways to enhance this thing, yes.
Yeah, with the increase in processing speed, cores and all, I don't see why performance would be a reason to actually use such a complicated algorithm.
Yeah, it's really more for, can you increase the efficiency of the data?
You think SHA-1's not adequate?
No.
Because
considering NIST.gov has banned the use of it.
Yeah. So
creating a hash collision,
you're still on the hash collision
versus
thing,
having a random 2 blocks collide are 2 different things, they tell me.
We can calculate later exactly, but I think you supposedly have a higher chance of getting struck by lightning 6 times versus having or something like that type of thing.
There's more data in the world than people to be struck by lightning.
Yeah.
Obviously, there's enough data, and but in essence, like I said, the actual integrity of the data is accepted as a top-notch, basically. This is actually a demo that we showed back in 2010. This was a system with 20 front-end nodes, 40 back-end nodes, if you remember the wind tunnel that we walked through. Right. It was 4 racks, 16 nodes. Each one was rated at 500 megabytes per second. So 20 times 500. You can see this measured externally as well as internally, 10,000 sustained. So very linear performance. You can also see on the Hydra GUI, everybody bunched up at right around 500 megabytes per second. And when we looked at CPU, you can see every one of them being about 90-95% CPU utilization. So very effective algorithm, very effective performance. Today we will actually show you basically the Hydra 4 hybrid nodes. We only put a couple of them, but we'll show you the linear performance across them at 40 terabytes an hour or 11,000 megabytes per second per node.
Is that 40 terabytes of deduped data or
yes, it's coming in, basically flowing in 40 terabytes per hour.
Not real data in like first.
No, real data in 40 terabytes.
Okay.
On the back end, we have to store a lot less because otherwise we can't keep up. Even from a physical perspective, we can't do it. So the only way is with the efficiency. We'll show you that. And in essence, each one of those nodes has higher performance than these entire 20 generation 2 nodes. So I think we've come a little bit of a way beyond back in 2010 on that side. So we'll show you something that shows twice as much performance with 2 nodes instead of 20 nodes. Okay. This is just a quick rundown of showing you comparisons of performance. As I mentioned, with dedupe transfer, we are at 40 terabytes an hour per node max, which we will show you today. You can see the claimed numbers across vendors on a per controller, and that's why we, in essence, state that we're the top single controller performance.
So Gideon, what's dedupe transfer?
Dedupe transfer does deduplication on the media server within our plugin. So the same thing as what we do on the accelerator node, we actually do within the plugin to prevent a lot of the data from even hitting the HYDRAstor.
This is like an OST option, or this?
It's an OST option, okay. Yes.
It's basically if you weren't transferring any data over the wire and you were just transferring hashes.
Correct, because you're catching. If you're, I mean, the higher the dedupe, the faster the speed. So this is obviously for highly duplicative data. And then if you're looking at the maximum scale out, then it obviously looks a lot more ridiculous because we can go up to 165 nodes or to petabytes per hour, or in essence over a terabyte per second, versus the competition, which either has single controller or multiple controllers, but can only do so many of them. So the scale is pretty significant in terms of how far we can get. But the other key thing goes back to the question, how many nodes can we start with? We can start with 1. So you can actually start with something this small that plays along these lines, but you know you can actually grow all the way to this level with this same type of enterprise technology.
What's your non-dedupe transfer speed max?
Non-dedupe transfer, without dedupe transfer, with Express I/O, which is a lightweight protocol for OST, we do about 6.3 terabytes an hour. And then with standard I/O without OST at all, it's 4.9 terabytes an hour for duplicative data. And then it becomes slower if it's basically 100% unique data. It gets to a little bit of over a terabyte per hour when you're purely bound by the spindles.
Just real quick.
About 1.1 terabytes an hour. Yes.
Just real quick, dragging it back to the collisions and the hashes, right? I just did a quick bit of math, and it turns out that, if I'm right, no, Howard's pointed me to something.
Guess what we'll be doing at lunch, you know?
Yeah.
Okay.
The chances of getting a collision apparently are 10 to the 50th, or over 95 good. Exabytes worth of storage.
Yep. So yes, there is a. We're getting close to that.
How many exabytes are you storing so far?
Well, a single 165.
No, all worldwide.
No, that's what I'm saying is what I think was it 6 or.
Yeah, it could
be. But this would be within a single cluster, right?
Correct.
But going forward, that kind of data is not unthinkable on a single cluster going forward.
And assuming, yeah, I mean, a lot of things have to hit right for that to happen. I mean, you almost have to be intentionally working very hard to try and create that collision. So.
Anyway, sorry, with the discussion.
I mean, it was a bigger issue back when people were using like MD5, you know, that type of thing, where it was 128 bits. it was more plausible, and that's why most people switched to SHA-1.
Okay.
Okay, so this is from overall in terms of how far we can grow. Also in the background, Inline actually, as we deduplicate the data, we also do application-aware marker filtering for major backup applications. Back when we talked last time, I think we had NetBackup and Simpana. We've added TSM, Networker, Data Protector, RMAN, System Recovery from Symantec. All of those, we do special filtering for the format awareness of those applications. For other applications not listed here, we actually still get very good dedupe, but we have less of a reason to create this special filtering for them. On a replication for disaster recovery, we support the WAN-Optimized replication. These can be different size systems. We can also go across between, in essence, from one accelerator or hybrid node or mini Hydra to another. We can go bidirectional. This is asynchronous replication. You can control multiple things, including throttling. You can throttle per replication set. You can throttle per node. You can throttle per system. And then you can also schedule and control when it happens and how often it happens, whether you do it once a day or once an hour, once every 10 minutes. You can control all of that.
That's passed before, back and forth is hydrated, as it were?
No, so this is why we call it WAN-optimized or deduplicated replication.
So it's
inside, just like we talked about the hashes being passed, same type of thing across systems. So we track which chunks of data have changed since the last sync point. Huh? Sorry.
So you're passing the hashes back and forth to see if the data is already there?
Correct. Because you can have either the data created locally or you can have another system passing that. Yeah. So we've actually, I mean, extreme case, it's not very often, but we have had in a customer situation more than 250 to 1 reduction in the amount of data that needed to traverse over the wire because of that. So in essence, we'll actually just pass the hashes that changed since the last sync point. Yeah. And this one will respond and say, hey, I only need these particular ones. Everybody else I have. And then that will get compressed and sent over the wire. So only unique compressed data goes across the wire. Sounds good? All right. And mind you, the other thing, in-flight encryption, you can turn it on or off depending on whether you have a secure wire.
The 10 to the 95th now is multiple clusters that are replicated together. Yeah. It's got to be a unique hash across all the clusters that are replicated together.
Okay. I'll quickly brief over this. Nobu will talk about it some more in a minute. I mean, I'll be done probably in about 5 minutes. But for OST, what level of OST the question came in, we actually, I mean, this is actually a little different than most vendors. We actually allow you to either get the whole OST suite, or you can actually license these one by one, depending on which ones you want. So you can license these individually. Dedup transfer, we talked about deduplication on the media server. Express.io is our lightweight protocol.
I'm sorry, go back to replication. Is it on a file system basis? Is that?
Per file system basis, you decide which ones, and you can control everything that I talked about controlling on a per file system as well. Yeah. So dedup transfer is the deduplication on the media server, sending only unique compressed data across, as well as the hashes. Express.io, lightweight protocol that improves performance over just traditional NFS or CIFS. So that replaces that. Dynamic I/O is somewhat unique to the HYDRAstor architecture, is the ability to actually go across multiple nodes and distribute the load on the front end and still have global dedup on the back end and have that done automatically. The other things that we support, optimized synthetics. So for those who are familiar with full synthetic backups, with optimized synthetics, we actually offload the synthesis or synthesizing off the full backup to the HYDRAstor side. So rather than the media server reading the previous full and reading all the incrementals, synthesizing and writing back, we eliminate all this workload backlog on there. Through OST communication, we'll actually do everything on the HYDRAstor side.
Is optimized synthetic something that has to be licensed in your environment?
Yes. All right. So everything, all those, I mean, the only one, the dynamic I/O, we actually provide at no charge. Okay. But yeah, each one of these can be licensed separately or as a package at a slightly lower price. And then and you asked about AIR, so we'll support, first we optimize copy or optimize duplication to get a single catalog update for multiple copies automatically with our replication technology, as opposed to doing it brute force by the media server. And with AIR, obviously also the auto import into a separate catalog and a separate domain. So this one, I'm going to skip past this one. If there are any questions, we can address them when Nobu goes over that. Physically, we have the hybrid node and the storage node. Those are the building components. We talked about the throughput for standard, maximum with Express I/O, maximum with dedupe transfer, raw capacity 48 terabytes. These are 12 3.5-inch drives, and then either 1 gigabit or 10 gigabit connectivity. And then the storage node looks like exactly the same, but actually just provides you the capacity, nothing else in terms of connectivity or that accelerated node function. We also offer a mini Hydra. This is a single node system that does not scale beyond a single node. So that's for small and departmental. You can see on there, these are actually 2 terabyte drives. So 8, we can actually cap them at 8, 16, or 24 terabytes. And then performance, 3.2 standard, 3.6 Express I/O, 19.8 for dedupe transfer.
So that's single controller.
Yeah, just one small one, and you can decide 8, 16, or 24. If you're going to grow, you don't want to start with this. So looking at the whole lineup, you can start as small as just a mini Hydra. You can start the grid with a single hybrid node. You can also have an HA type configuration with a 2 and 2. And you can continue to go across up to 11 racks. We do provide also HYDRAstor racks. That's easier for us because it's fully labeled and all the connections are there. But if you insist on your own racks, we can do that as well.
But on the single node one, right, even if the node was to die, like the motherboard fried and melted or something, because you erase your code, even the hash tables and stuff, you could replace the board, and as long as you got the same drives, you still got access
Absolutely,
to
absolutely, okay. Yes, correct.
We used to call it the mind melt.
Yeah.
And obviously, if you have enough nodes, you can also, if you want to do certain maintenance, you can just take a node down. Everything continues to run because you have enough resiliency. Yeah. Bring it back up, it automatically synchronizes everything.
What are your path to tape options?
So path to tape, that's an interesting one. So all the connections on this are 1 gig or 10 gig. Typically, what our customers do is obviously the path to tape, they don't need to do that as often. They maybe do it vaulting maybe once a month or however often they do that. The media server would read the data and then write it to tape. There's no direct.
Through which method? 3-way NDMP, or is it just image copy?
Yeah, just, I mean, it has it in its catalog, the copy, and it also has access to a tape library or whatever it is. So we just read the information from that logical unit, or in OST LSU or a file system, whichever. Yeah.
Do you plan to support an object storage interface in the future?
You've been in the Object Store Summit, didn't you?
Yeah.
Yes, so we actually are working on that. We're working on a couple of protocols, S3 and OpenStack Swift. All right, so over here we show you actually don't even need 165 nodes to achieve 165 HNs to achieve the max performance, because a single HN by itself, because of the way we do the hash table, it can actually get additional benefit from a storage node. So depending on how many, and the balance works out that with 104 hybrid nodes and 61 storage nodes, you should be able to achieve a similar performance to 165 HNs. But you could have a model that's a 4165 as well. But in essence, can grow all the way from a handful of terabytes an hour to over petabytes per hour, and then also the capacity as well. Up to 8 petabytes of raw, traditional typical policies, retention policies that would translate to over 100 petabytes of information. All the data is actually for Hydra, the HS8 and the HS3 is actually common code base. Other things I didn't mention before, but things like snapshot or cloning capability is available at no additional charge. Somebody asked earlier about shredding. We do have the shredding built in as well for classified information. And then some of the other, these are the optional features over here. So we have the WAN-Optimized replication, we have the worm capability, and on the HYDRAstor we do support both enterprise as well as compliance worm. So with a compliance worm, you cannot delete the file system. It's pretty much stuck over there. And then for the OST, either individually or as a group, those can be licensed. From an overall picture, do backups, archives, content depots, repositories to a system that can scale to pretty massive scale, and then replication across different types and different sizes of systems. A couple quick things I'll go before we do the demo. Earlier this year in July timeframe, we also announced the HS6, which is a slightly defeatured version of the HS8. Still gets you from 1 to 165, does multi-generation expansion, erasure coding, but then the cost point is between 1/2 to 1/3 the cost of the HS8. So this is primarily for archive type environments or content repositories. The deduplication, rather than variable size, it's fixed size on this one and bigger chunks versus the other one. That's kind of the defeaturing of that. But it also includes the compression, also has bundled in global namespace with that. For this platform, there is no OST integration, so that's another piece of the cost point. And then we also offer...
The fixed chunk size duplication is because you have also less CPU and...
Yeah, we also have slightly reduced the CPU level. So yeah, I mean, kind of several different things. For archive environments, if it's not a specific, if you're not getting much of a dedupe to begin with, then it's not going to make a big difference. And if it's the same exact file, in both cases, you'll be able to deduplicate. So for certain environments, this makes a lot more sense because of the cost point. And then for this one, we also offer the optional high-speed image compression for bitmap files based on our own technology. All right, so this is the lineup over here. Over here, the performance numbers are based on 100% unique data. So that goes back to how fast we can write when we actually go just based on spindles. At that point, it's 1.1 terabytes per hour per node. Doesn't matter if hybrid node or storage node. It's just how many more spindles can I get. So obviously, if you have duplicative data, these numbers are going to be much higher. But for non-duplicative data and 50% compression, you'll get this.
Are you using your own dedupe algorithms or someone else's?
This is our own. Everything is our own technology. So we're still spending quite a few dollars. So this is more than $20 million per year. In fact, more than $25 million per year on HYDRAstor.
The compression algorithms are not yours.
No, the compression. Okay. Yeah, the compression is LZO compression.
Right. Okay.
I mean, it's available. I mean, there's really no reason, and it's not something you have to pay for separately. Yes.
No, just when you said it's all yours.
No.
Like, whoa.
No. Yeah, and the Linux writing underneath is not ours either. But all the unique stuff on top is all ours. Yes.